The broadcast is now starting. All attendees are in listen-only mode.
All right, Paul, you can jump right in.
Good afternoon, everybody, and welcome to our next edition of Just Ask Paul. So this is a series of questions that individuals have emailed, and I have researched some of the questions. Some of the questions come from experience in other areas, and some of the questions have come from other people within our industry, some of the answers. If you have questions, I'm going to ask this again at the end of today, please email them, and I would be happy to address them. So to get right into this, first off, my name is Paul Brancleon. I am the Director of Research, Education, Technology here at NADCA. And we're going to go through a series of questions and answers to each one of those questions. So the first question is, how can I verify automatically if the squeeze pins are working properly? So just a 2-minute background on this. So we're going to be looking at squeeze pins, the operation of those squeeze pins, a stroke of the squeeze pin, and squeeze pin depth is really what we're after to know that the squeeze pins have functionally worked. So to understand squeeze pins, I just pulled some stuff from some research that is from 2018 just to illustrate what squeeze is. So we have our aluminum or zinc or magnesium being filled into our die casting, and we have thick areas of the casting that are going to solidify last, and we use a squeeze pin to move into that area once the area is full of material to shrink the porosity, to feed that shrink porosity that's going to exist in those areas. So when we're dealing with squeeze, we're dealing with basically 4 things. And we've got a graph here on the left. This graph shows the injection of the material. Then once the injection is completed, we're going to have the squeeze start. So when the squeeze starts moving into that area, now remember this material is starting to solidify, and then we're going to have the duration of the squeeze, and the squeeze is going to stay in the entire time until the die opens, and then the casting comes out. And so we're going to have some delay from end of injection to start of squeeze. So we're going to move that pin into those areas. So moving the pin into the large, dense areas to feed the shrink that's going to exist in those areas that can't be fed from the intensification of the die cast machine. And we're going to want some optimized stroke length of those pins. We don't want the pins to go to depth. We want those pins to stop by the metal, because then we know we're completely filling that shrink that's going to exist. So the question was, how can we verify that the squeeze is actually operating? Unless we check squeeze depth manually, and we have a minimum squeeze depth and a maximum, and if we hit our max or past our maximum, we know that the pin has gone completely to length. If the pin goes all the way to depth and the metal doesn't actually stop the pin, then all that pin is doing is acting like another core in the die cast die. So we want that pin to actually stop. I've used these type of switches. So this first one on the right, just a double throw color hammer type switch. This is a Honeywell that it's going to give us the squeeze, and it's going to just show that the squeeze has moved in. And if you can get 2 of these on the back end of your squeeze cylinder, and then you can know that it moved past its minimum and it hasn't reached its maximum. I've also used these high temperature micro switches. Omron has one, Honeywell has one, and you can use these type of switches in front of the squeeze cylinder to actually show that we've reached our minimum depth. It doesn't have the ability to tell if it's gone past its max. So with the squeeze pins, we can use micro switches, double acting switches, color hammer, E50N1. And the other way to do it is to physically measure, so the minimum depth of the squeeze pins. So we want to make sure that we're past our minimum, but we haven't gone to a maximum depth. Once again, otherwise it's just acting like a core pin. Moving on to our next question. The next question is, how effective is CT scanning of die-cast aluminum parts? specifically regarding dimensional accuracy compared to a CAD model? And can you recommend a metrology company with this capability? So first, I'm going to answer the question, and then I'm going to go through some detail of the question. So the first point is CT scanning is computer tomography, and what we're doing is we're X-raying in a 3D fashion. So we're scanning the part using X-rays. Typically, CT scanning is used to identify internal defects. So we're going to look at some examples of CT scanning. We're going to show porosity in that 3D. So what does it look like when you CT scan a casting, a die casting? And then I'm going to show you that it can do some geometry. But when you're using geometry using a CT scanner, you have to know the focal length of the device. So you've got to know the distance between the X-ray source and the image intensifier to actually know that the image you're getting has some dimensional accuracy. If you don't know that information, or that part can be placed in various locations inside the CT scanning cabinet, and it's not placed precisely, then using that for dimensional accuracy is very difficult. There are better methods to use if you're going to be using some 3D imaging, and we're going to touch on one right at the end of this, and that's done by ARIS, and that's a project that NADCA currently has ongoing. So to touch on all of this, I first want to just show you, this is CT scanning of a test bar. So this is a die-cast test bar. This is called micro CT scanning, and we can see porosity, well down under 1/1000th of an inch. So we're seeing all the porosity in this particular sample, and so this is CT scanning of a test bar. When you're looking at that particular test bar, we can then get data from that. There were 64,000 pores within that sample, total volume of 28.4 cubic millimeters. So the average porosity content is 1.3%. In my experience, casting less than 1.5%, a normal standard die casting, not a squeeze casting or a structural casting, under 1.5% porosity is pretty normal. When you get over 1.5%, then you've got pretty excessive porosity. So this particular sample is not excessive. It does look that way, but remember, we're looking at every pore, all the way down to 1/1000th of an inch. This is another specimen. So this is a test specimen. This is one that I did last week. So we CT scanned it because we wanted to see the porosity prior to actually breaking that sample. And we can see the various porosity. We don't have, unless we measure the outside dimensions, we don't have any sense of how big these are in this particular CT scan. So when we're looking at a CT scanner and we're measuring, or we're going to use that for testing geometry, can be done. So this particular CT scan is CT scanning a casting, and it's actually looking at the 3D geometry. Now, once again, you got to know a lot of data as far as where this is positioned in the cabinet, the distance to the image intensifier and the X-ray source, so that you can actually go on to that part and get some dimensional accuracy. I would not recommend this for a way to measure castings. Companies that can do CT scanning, the first one I want to mention is BJ Technologies. Their information is here. It's vjt.com is their website. They're capable of doing CT scanning. They also produce X-ray machines and CT scanners. Another company is Jesse Garrett Metrology, located in Detroit. So Jesse Garrett, and you can contact them, sales at jgarrett.com. Another company is North Star Imaging. North Star Imaging has 3 sources in the United States, and there are multiple sources around the world. So they've got a group in Minnesota, California, and Massachusetts. Once again, this is North Star Imaging. So those are 3 sources for CT scan Some of these guys just do imaging, like Northstar. Some of them, like VJ Technologies, physically make the equipment. So this next thing I want to show you is kind of away from CT scanning, but we are doing a project where we are 3D scanning die castings. And this is a cobot, this device here, and we've got a 3D scanner unit on this. And in just a second or so, you're going to see lasers now come on. So we've got lasers here. You can see this red light. And this device is now starting to 3D scan, dimensionally scan the die casting. Once this casting is scanned, we can compare this against a CAD model, and we can then determine variation from the CAD system to the 3D scanning system. So if we were looking for just information on dimensional accuracy of a die casting, I think this type of a system is much more accurate, much more applicable to measuring die castings than a CT scanner. CT scanners is going to be much more adept at porosity and determination of internal quality on a 3D basis. So you can, in a 3D sense, tell where that porosity is at. So once again, this is ARIS, and they're currently working on a NADCA project. And the project is to eliminate CMMs as the only way of measuring castings and to quickly set up and 3D measure die castings. So we've got Chrysler and Ryobi, both our partners in this, and we're using some of their die castings to determine the applicability of this as compared to doing CMM readings of die castings. Okay, on to our next question. Is there a best practice specification for excising tensile bars from castings? What sizes are those? Are they using rounds or flats? And what a location? The easiest locations to machine tensile bars from castings is typically the thick sections. However, most of the time, tensile bars taken from these thick locations do not reflect the casting's general mechanical properties. And I agree with that. So we're going to talk about that. So first off, NADCA has a project where we are taking castings of various alloys and we're excising test bars from those castings. This is a multi-year project, and currently we have done samples from A380 and B360. And with the B360 samples, we checked them in the F condition or the raw condition and in the T7 heat-treated condition. The current alloy being checked right now is A390, and these parts are being cast, and then we'll be taking samples from those. So of the first two alloys that have been completed, we took samples of 2 millimeters, 3 millimeters, 5 millimeters, and 8 to 9 millimeter cross sections. So when we got to that 8 to 9 millimeter cross section, we definitely saw a difference in mechanical properties. So let's start from the beginning of the question. What's best practice? Well, best practice would be to use some sort of die cast tensile bar. So this is just an example of tensile bars that are being cast, tensile specimens. NADCA has its own mold. I don't have a picture of it, but NADCA has its own mold. We call it NADCA 1, and it casts standard ASTM test bars. So that mold is available for die cast companies to use. Currently, that mold, I think, is in Michigan at a die caster. They just got done running it several weeks ago because they wanted to test one of their alloys that they were casting. The next best practice, and it's done by a lot of structural die casters today, and that's going to be cut the test bar specimens from the die casting. Now, if you're going to do that, you're going to have flat specimens, machined on only two sides, with two sides being die cast. And from the research that I've done, the 3 millimeter to 5 millimeter sections are going to result in the most uniform mechanical properties. So this is a die casting that I completed. This is a rear end motor mount housing for a marine application. And this is B360 alloy. From the sidewalls of those castings, we excised samples. Now, I couldn't get down to a 3 millimeter sample, but I got to a 3.5 millimeter sample. And I physically had these water jet from each one of the castings, and you can see the tensile bars. Once they're water jet, you can just break them out. And then they're only machined on two sides with skin left on two sides. So here's a little bit closer example or closer picture of those specimens. And so if you're just doing one or two, you would just take a die casting and you can have these CNC machined. Water jet machining is probably a little bit better because you don't have any thermal contribution from the potential cutter onto the specimen. Okay, so here are some data points from the 3.5 millimeter test bars. This is the as cast condition, and this is the heat treated condition. So we're right around 21 KSI to 22 KSI, and that would be our total range with a mean right around 21.4 KSI. And then once we heat treat it, we do lose some yield, but we maintain that range. Now, I did a minimum of 30 test bars, so we got a good statistical sample from those parts. This is the tensile, so we looked at yield. This is tensile, once again, non-heat treated and heat treated. And then this is the elongation. So we did the mechanical properties, tensile, yield, elongation, and we can see as cast, we were right around 3%, 3.5% as a mean with the range of 30 samples. And then once we heat treated this, we got upwards of 13% elongation. So just showing the mechanical properties. And I also did 5 millimeter samples. And once again, these were water jet out of the specimens. So here's a comparison of the 3 millimeter and the 5 millimeter data. So as we look at that, we can see the yield, 21 KSI, very similar. 17 heat treated. The tensile, ultimate tensile strength was 34 KSI, 33 on the 5 millimeter specimens. Once again, very similar. And then 28 and 29 KSI heat treated. Once again, very similar. And then we can see the elongation. Elongation of the non-heat treated right around 3%, 2.8%, rising up to 13% and 12.5% once you heat treated them. So very similar data. So cutting thicker sections. So this is just about the 8 millimeter cross section that was then water jetted out of the castings in a very thick section of the same die castings. So when we look at that, we look at the 3 millimeter specimens, the 5 millimeter specimens, and then the 8 millimeter specimens, treated and heat treated conditions, and then the elongation. Once again, because of defects in those thicker sections, we didn't get the elongation response that we got from the thinner sections. So my recommendation, once again, would be to stick to the 3 to 5 if you're going to machine specimens out of the die castings. So these are the 8 millimeter specimens. Once we evaluated them and try to determine what took place, we can visually see the porosity in the broken, these are the test bars, in the broken sections. We then took some photomicrographs of those sections, and we can definitely see porosity where we didn't see it in the 3 and the 5 millimeter cross section. So as a quick summary, if it's possible, cast the tensile bars. It's going to give you the best uniform properties. It's going to give you a good skin effect around the entire round tensile bar. If you don't have the ability to cast those tensile bars, water jet them. So water jet those out of the square sections or machine the specimens. I would stick to 3 to 5 millimeter gauge, that's thickness on the sections. And then you need to be aware that if you have a large range, you're testing 10 samples and your 10 samples are moving all over, start looking at porosity or inclusions, because they're going to definitely affect the outcome of the mechanical data if they're present in your specimens. So the quality of the die casting is important to make sure you've got very little porosity and very little or no inclusions. Any inclusions are going to affect the mechanicals. So moving on to our next question, question 4. Our casting dies have several core pins that tend to break periodically. We rely on machine operators to visually inspect these castings. Visual inspections are not 100%, therefore many scrap parts are made because the visual inspections fail to detect the defective parts. We also have core pin fixtures that are used twice per shift to check for broken core pins. Oftentimes, many scrap parts are made before a broken pin is detected using these methods. I've recently started investigating industrial metal detectors used in the food industry to possibly detect the steel core pin in the as-cast part as it comes out of the die-cast machine. So my question is there a more reliable method used in high-pressure die casting for detecting broken core pins in the die, detecting the scrap parts, or detecting the steel in the as-cast parts? Very long question. So let's talk about that. So the first thing I want to talk about is we're looking for some sort of poka-yoke device. Poka-yoke device to check that the cores are present and that we don't have any broken cores. So in my past, I have cast parts with very little cores, or have cast parts with upwards of 40 to 50 cores in a single die casting. Broken cores are definitely a risk, and so it comes down to, are we doing hourly checks? Are we doing twice a shift checks? If we are, then our method is we're going to then go back to that last known good part. We're going to contain those parts if we find a broken core, and then we're going to sort the balance of those parts, making sure that none of those escape containment and they don't get to our customers. Other methods that we're going to talk about are mechanically checking of the pins in the die-cast die, and doing some sort of electronic testing for those pins, or we're going to check the cores of the die castings. So our choices based on our company's decision is risk and risk management. So how much risk are we willing to take? Are we willing to produce for an hour? Are we willing to produce for 4 hours? And then what's the cost? What's the cost of those man hours when a broken core does happen? Or what are those capital costs for putting in detection devices to detect for the broken core in the die-cast die or the broken core in the die casting? And then what's a return on that? Our risk versus our cost. So determining all of that is a company choice that we've got to make. So the first thing we can talk about are sensors. Sensors to prevent the processing of those defective parts. So we can use limit switches, and we can physically probe the holes. We can use proc sensors, and that's pretty much what you're talking about. Using a steel sensor to check for a steel component in the die casting. Now, I personally have looked at that in the past, and you're looking for a needle in a haystack. The casting with the broken core in it. Sometimes it's very easy to find, sometimes it's very difficult to find. But once the core breaks, every casting after that is going to have the broken core. So another thing that has been done, and several die casters are using, are infrared or laser sensing of the die cast die itself to check the presence of the cores or critical cores. So when we're looking at laser sensors, there are several different types of sensors out there. If you want to email me, I can send you some sources for these lasers. But these lasers have the ability then to measure from a distance for the presence of a core in a die-cast die or a core or punch in a trim die. So the one drawback of using lasers, if we get a partial broken core and the laser is sensing, the base of the core, and then just the tip breaks off, the casting is still going to pass. So it's going to allow it to produce with a partial broken core. Other systems, and I've used these, So I've used a vision system. So vision systems can just be as simple as a camera looking for light and dark areas. So you take the casting, you put the casting in a fixture, the camera takes a picture. If the core is there or the core is not there, it can actually sense that depending on the scalability of the camera. So how expensive the camera is, higher resolutions can actually check the core and core depths. But once again, the drawback is a partial broken core can be passed by a vision system. But vision systems are ways to check for broken cores on an automated system using 100%. You can also use an LVDT. Now, I used this a long time ago where I had a casting with many cores in it, and I would just fixture the part. The operator would get the trim casting, put it on the fixture, throw a clamp on it. The LVDT would come up into the part and check all of the holes. Not only do they check for the presence of the hole, but they have the ability to check for the depth of the hole. So you know if you've got a partial broken core or if the core is completely there. Problems with this is these sensors are large. So if your cords are close together, you may not be able to get all the sensors in there. Fixtures are necessary, and if you have multiple cores, multiple LVDTs are going to be required, and there is some cost associated with that. So my recommendation, look at the frequency of your hole checks and the hard gauges you're using for those. Is it better to certify, your critical holes, or to go to your hourly checks, or every 4 hours that you're doing right now? You've got to be able to use pins or core pins or gauges that must go to depth, like a flush pin. You can use laser sensors aimed at the die or the trim die to detect the presence of broken cores. Vision systems can be used. They can be costly, but they can do a 100% check, and then LVDTs can also be used. So there's several ideas for checking for broken cores or the presence of broken cores. Moving to our next question, and that question is, has there been work in the United States on electrostatic dry lube coating and applications for the high pressure die cast process, and some references? So let's start with references. So these are two companies. Hill & Griffiths is a US company, and they have a lube system, and they have experience in dry lube, in electrostatic spray. Luberline is not, I don't think they're a domestic, but they do have a presence here in the United States, and they also have a material for electrostatic spray. So electrostatic spray is where it efficiently charges the spray, and then the tooling is typically grounded, and then those charged particles that adhere to the tooling. I'm going to play a quick video, and I think everybody can hear this. So you can see we can spray. Normal spray can hit areas of contact. Electrostatic spray can actually wrap around. And then if it's a mist, it actually gets better coverage in a wraparound. So here's some examples of that. We're going to want a very fine mist with some sort of a vortex to that mist. So here's a die cast application. So we've got a die casting. Once the casting is pulled out, we're going to see the electrostatic spray come down. And we're just going to see this little bit of blow off, and then a fine mist being applied to the tool. Okay, this fine mist does not do any cooling. So if you're relying on spray to do cooling, this is not going to help If you've got soldering conditions, this is not going to help you. So here's some advantages of using electrostatic spray. So really quickly, we're using some sort of charge device to charge those particles, those very fine spray particles. The dye has the opposite charge, it's grounded, and then we're getting an adhesion of those lube particles to the dye electrostatically. Has the ability to wrap around. So rather than spraying from multiple locations, these charged particles have the ability to wrap around and spray completely. So when you're spraying down into hidden holes, if it's electrostatic, you can get adhesion instead of having any material bounce off or get blocked because of air turbulence. Here's another quick video just to show how the spray works. So we can see that charged particle head, and you can see you're getting some wraparound effect when we're spraying it onto a negatively or positively charged, a grounded device. So we can see that being sprayed from one location on the left, and we're getting complete adhesion around the entire perimeter. Here the spray is directly opposite us, and we're getting that spray to go all the way around that material. Okay, so we get the sense of what the electrostatic does. Here is the Hill and Griffith material, this Drycolube. Some drawbacks of electrostatic spray is that all the dye heat must be removed internally. You've got to have good cooling, good engineered cooling to remove the heat from the tool. If you've got solder formation on the face of the tool, you can't just reposition a sprayer to cool that area. Electrostatic spray doesn't work that way. Once again, it's got to be internally cooled. So we could have heat holes, we could have flow defects in the process if we don't have sufficient internal cooling, or if that internal cooling is being blocked through lime or deposits in the cooling. So if you've got current tooling that's been designed to use water spray, sometimes it's very difficult to convert that tooling over to electrostatic. You've got to make sure you've got a good thermal balanced dye, then you can use electrostatic spray. On to the next question. And this is the final question for today, is what is jet cooling and what situations is it used for? So jet cooling is a very good way to cool very small cores or specific areas of the die-cast die. Jet cooling technologies offer the die-caster the possibility to control temperature on critical areas and minimize the possibility of shrink porosity in those areas and in small cored areas. So we use jet cooling, and we have a core or a detail with a very small bubbler-like tube that goes down inside of there. And so we then have an apparatus. So we have this device where we've got water being fed to it. And then we have the jet cooling. So we have the water being fed into the mold, and this water is under pressure, anywhere from 45 to almost 300 PSI. It then gets fed into a core pin, very small orifice in the core pin, and it flows in and then flows out. We've got a return line. And so this device can do multiple cores depending on the size of the device. Bigger devices can do more cores, and so you can have multiple jet cool components in your tooling. So the way this works in the process is during the casting phase. So we start the injection, we're actually filling the cavity that's when we turn the jet cool water on, and we get this high pressure water cooling. And once again, it can get up to about 20 bar, which is right around 290 PSI. And this cooling only stays on while we're solidifying the casting. Once the casting is solidified and ejects out of the mold, we then purge all the water out of the tool. So we're not continually cooling down those jet cool components. So we then purge all the water, and then some units have the ability to check for core breakage, and then the cycle starts over. We inject metal, we then cool while that solidification is taking place, we purge during ejection, check for broken cores, and then we continue the cycle. So what are applications? Well, applications can be where we have shrink porosity due to heat, and we have a core pin where we can't get a bubbler down in there, but we can get a jet cool in there. So by doing that, we can actually cool that area and move that shrink or feed that shrink, get it to solidify, and move that shrink away from that core area. Here's a quick thermal video of a core pin, and you can see it's hot. Now the jet cool's turned on, so it rapidly cools that core pin. And so jet cooling has the ability to cool very small areas. There are die casters out there that only use jet cool. They don't have any process water or hot water systems, and they are using these type of devices to cool their castings. So that was all the questions that I had for today. I do have a couple more. If you guys have more questions, please forward them. You can forward my email, or Athena had already sent out a questionnaire. You can respond to that. So if you have additional questions, I will answer those questions and then get that data back to you in our next edition of Just Ask Paul. So right now, I'd like to open this up to questions. If you have questions, you can actually type those questions in, and I can answer those questions.
Thanks, Paul. So as Paul said, we are going to open it up for questions. There are a few ways that you can ask questions if you don't know how to do that already. Within your control panel, there's a text box. You can just click within that text box, type your question in, and hit send. If you'd like to ask your question out loud, and you have a mic set up, or if you're calling in on a phone, you can just click that little hand icon. We will go ahead and unmute you, and you can ask your question out loud as well. Last but not least, as Paul said, you can email him directly. You can also always add question to that questionnaires link. That is not only in the emails that you were sent, but also it's hosted on that Just Ask Paul page, along with all the old webinars that Paul has put on for us. So any of the old episodes are on there as well. So you can access those whenever. And then there on that same page is also a link to submit additional questions. And then we will put up when the next episode of this will broadcast as well. So with that, we're going to hang on the line just for a few minutes and see if you guys have any additional questions. Okay, I don't see any additional questions coming through. If you're in the process of typing something in, if you would just like to click on that little hand icon, that'll let you know that you're typing something in, and we should hang out on the line until that comes through. All right, I don't see any hands raised and I don't see any additional questions coming through. So with that, thank you everybody for attending today. Again, if you are looking to post additional questions to Paul, please feel free to either submit those to him directly or fill out our questionnaire and we will get to those in the next episode. And Paul, thank you for answering all of our questions today. Thanks guys and have a great rest of your day. Bye.